Excellent. So go ahead, please, Damien.
Okay, so thank you very much, Nima, for the introduction, and thank you for inviting me to give this seminar. I'm really glad that you are organizing this series. I think your building community, as you say, in this field is really important, because this field, it's so important to kind of understand the different layers and to be able to think a little beyond your original job. So yeah, I think these seminars are fantastic. So yes, so I'm going to talk about in-memory computing with unreliable devices, and I'm going to explain why I think it's a very critical question. And so I'm going to give some like broad consideration and also some example of my own works, which are all collaborations with the University of Aix-Marseille, so the groups of Marc Boquet and Jean-Michel Portal, and Letty in Grenoble, the group of Elisa Vianello. So I start my presentation with a little context, and I think if you've been following this series, this kind of things you have heard already, but yeah, just to give a little idea of where I'm going. So, you know, in recent years, AI has made so fantastic progress. So it's really a big driver for computing. And when you go to research conference, it's really AI everywhere. But there is one big problem with AI, which is its energy consumption. And it's fun actually to look at some examples. If you look at the self-driving car prototypes that have been so successful, the power consumption that is needed just for their AI is typically around 2000 watts, which is actually a significant contribution to the power consumption of the car. If you compare with a human brain has power consumption around 20 watts, which is not used solely for driving, but for all tasks the brain has to take care of. So you can see already there seems to be some inefficiency in the way we do AI, because brains are able to do similar tasks with much better efficiency. And it's even worse if you look at the question of training. For example, for training GPT-3, which is one of the most complex AI model ever trained, it's a language model, it required an estimated 200,000 kilowatt hour, which corresponds to actually 1,000 years of brain operation. So that kind of show you that AI is really very, very energy hungry. And that's actually a problem in real life, because due to that, most sophisticated AI tasks cannot really be done at the edge. They cannot be done in embedded devices. So you have to rely on the cloud, which causes even more power consumption and also safety and security issues. It's really important to understand where this energy is coming from. And we believe it has a lot to do with memory. Because if you look at a modern computer, actually memory access is very big cost in energy. And most people know that, but do not necessarily realize the extent to which it is true. And to give an example, here I plotted example from a modern computer. So if a modern computer, if you need energy 1x to add 2 integers, and you compare with the memory, with the energy that is required to access these 2 integers in memory. If the 2 integers are stored on the cache, so on chip with the processor, it actually takes 60 times more energy than for adding them. And if the 2 integers are actually stored off chip in a dynamic RAM, it takes 3,000 times more energy than adding them. So you realize accessing data from memory has become a lot more expensive than actually doing arithmetics. And when you do AI, unfortunately, you have a lot of memory access, because AI is a world of big data and models have a lot of parameters. And by contrast, in AI, you don't have that much arithmetics. So when you do AI, you have to pay a lot of this and actually quite little of this. And it's very fascinating to compare this with the brain, because the brain is very different situation. In fact, in the brain, memory, which is mostly supported by synapses, is located precisely where you need it, precisely where computation happens, which is mostly done by neurons. So that means that the brain really does not have to spend this kind of memory, this kind of energy to access memory that is very far away, because memory is right where it needs to be. And because actually brain has a lot of memory, in fact, there are more than 10,000 times more synapses than neurons in the brain, I like to think of the brain a lot like a very big memory where you have computation that is a little scattered everywhere. And so we can say, to use a word of these seminars, brain is to some extent a champion of in-memory computing, And following this trend could be a very big idea for reducing dramatically the energy consumption of AI. And for this, we have a very big opportunity right now, which is happening in the world of microelectronics. Because in the world of microelectronics, you actually have new memory devices that are emerging that are quite fundamentally different from the memory devices we have today. So these new memory devices have so they are based on nanotechnologies, and they have the particularity that the memory state is really in the electrical resistance of the device. To change the memory state, you change the actual electrical resistance of the device between low resistance and high resistance. And this can be done using very different physics. So you have memory-resistive devices that function by actually moving atoms. You have phase change memories that phase change the material between crystalline and amorphous, or you have magneto-resistive devices that function with very tiny magnets. But they are all this kind of resistive memory. And these technologies are really nice because they are very fast, maybe not as fast as RAM, but almost as fast as RAM. And they are at the same time non-volatile, like flash memory. And also, unlike most current DRAM or flash technology, these technologies are really compatible with CMOS. You can embed them in the back end of your CMOS, and so have your memory very closely integrated with CMOS, even in very advanced process. And so these properties, like fast access, non-volatile, can be integrated tightly with CMOS, really suggest that these technologies are really ideal for having this vision of integrating logic and memory very closely together. And in recent years, this technology have made fantastic progress, and they are now in industry at many major companies. However, this vision does come with major challenges. This technology rely on nanometer scale physics. Nanometer scale is where you start to see atoms. And when you have devices operating in this regime, it's very, very hard to have perfect behavior. So if you're resistive RAM, memory store, phase change memory function by moving atoms. And you can imagine that's something that is very difficult to do reliably. Magneto-resistive memory functions by switching a very, very tiny magnet. And that's also something that is never totally deterministic because of the properties of nanomagnetism. And in fact, to a large extent, these new memories can really, they are so stochastic, they are so imperfect, that they are really, typically, you need to describe them, you need to use the tool of statistics. For example, this is the kind of things people plot. So this is data from hafnium oxide, memory store, or resistive memory. And so the idea of these devices is that you want to program them either in a low resistance state or in a high resistance state. But each time you program them, they end up in a different resistance. So you plot the cumulative distributed function of the resistance you get when you program the devices. So for example, in this case, we program the devices with a pretty high voltage, which is not very favorable because it requires a lot of power, and also it's not very good for device endurance. And you see in this situation, we have low resistance that is quite tight, but high resistance that is not very well controlled. On the other hand, the two are still quite different, so you can still quite well do difference between low resistance and high resistance. On the other hand, if you use low programming voltage, you can see now that low resistance and high resistance are actually not that separate. And sometimes you end up with a device with low resistance, with a resistance that is actually higher than a device that was programmed with high resistance. So that means that when you program this device in this regime, you will see errors quite often. In this regime, you will actually still get some errors, but at higher number of sigmas, they are just less likely. And that's actually a very big problem. So this is, for example, data from Intel that they published from their resistive RAM or memory store process in the 22 nanometer technology. So you can see the memory stores are here in the backend of the CMOS, and the transistors are here. And you can see the kind of bit error rate they get experimentally. So you can see it depends. So after only one cycle, you have less errors than after 1,000 cycles. So 1,000 cycles means you have programmed your device 1,000 times. And also it depends on the temperature, it depends on many things. But what I want to insist is that these numbers, by the standard of digital electronics, are quite high. So you can see 10 to minus 6, 10 to minus 5, 10 to minus 4. So I really want to insist these technologies do come with errors. And of course, this level of error is unacceptable for digital electronics application. So what is done currently in industry is to rely on error correcting code. So that means that when you program your memories, you actually have extra memories that are used, that you program with redundant information. And this redundant information is then used to detect errors. And if errors are detected, then you have algorithms that allow identify where the error is and to correct them. And as a matter of fact, because these bit error rates are quite high, industry has to use quite strong error correcting codes able to correct multiple errors. So for example, in Intel resistive RAM and MRAM technology, based on their IDM paper, they say that they use ECC that is able to correct up to 3 errors per 128 bits. So if you look a little into the literature of ECC, you realize that decoding this type of errors is actually not that easy. It's a lot of operations that you need to correct errors when you have this kind of strong codes. So that means that, unfortunately, when you use this memory, if you have to use ECC, you are going to have a quite significant overhead due to the SSC to detect and correct your errors, and it's going to be quite costly in terms of delay, energy, and area. And to me, this is not entirely satisfaction, because I want to go back to my inspiration in the brain. In fact, the brain also functions with nano devices. So nano devices from the brain do not function with electrons and holes like in electronics. They function with ions, but it's still electric devices. And actually, to a large extent, these devices are very similar to memory nano devices. And in fact, the nano devices that the brain uses to compute are also extremely imperfect. So in fact, the brain using two types of nano devices. First, ion channels, which are some kind of memories that actually act as some kind of controlled ion current source. And if you measure the current in ion channel as a function of time, you will realize it's actually pure telegraph noise. It is actually pure noise. So not very good by standard of electronics. Other type of nano device that brain is using is actually the synapses, and synapses that also act really as memory, but these are also very bad nano devices. Actually, when synapse receives an input, it does not even always transmit it. And there are measurements in biology that show by how much synapses are failing. And you can see example of these measurements. So it actually depends a lot on the part of the brain or the type of synapses, but you can see that typically synapse transmits information around only 80% of the time. That's 20% failure rate. So that means it's like you have a memory and 20% time you read it, you actually don't read it. So that's actually not good at all. But to our knowledge, there is no mechanism in the brain that would still, when a part of the brain receives some input, like a study, use some ECC to identify if some spikes are actually erroneous spikes, and in case they are erroneous spikes, correct them. So brain probably does not use formal ECC, but still works. So in this talk, I really want to show it can be possible to embrace the statistical nature of emerging memories for doing in-memory computing in a way that would avoid ECC. That's really what this talk is about. And to make this point, I'm going to rely on 2 projects. The first project is I'm going to show circuits that work even if the devices make many errors. And these circuits are based on the concept of binarized neural networks. And then I'm going to show more crazy research, that is research where you kind of change your point of view on your memory devices and you embrace the statistical nature of memory stores. Instead of seeing it as a problem, you see it as a feature. And I'm going to show we can do actually learning and learn real tasks by using the imperfection of memory stores. So this is the program for today. Let's start. So in this first project, we are going to rely to make a system designed for doing low energy AI. And for this, we are going to rely on a concept which is called binarized neural network, which is a type of neural network that was invented in 2016 in the group of Joshua Bengio, one of the most famous persons on AI. And binarized neural networks, they really look like traditional neural network, but with a difference. is that synapses and neurons, instead of taking real values, like in conventional neural networks, they can only take binary values that mean either +1 or -1. So it's very simplified. But despite this, binarized neural networks can actually be trained to do quite complex tasks. In particular, on vision tasks, we can actually approach state-of-the-art on many tasks. And of course, binary neural networks are very simple because parameters are binary instead of real, so you are going to save a lot of memory. But also, when you do binary neural networks, everything becomes simpler. So in neural networks, you have to multiply normally synapse value and neuron value, which is multiplying two real numbers. But if you have binary neural network, then it becomes multiplying two binary numbers. And if you look in details, you will realize that actually only an exclusive NOR gate, one-bit exclusive NOR gate, which is very simple operation. Same in normal neural network, you have to sum real numbers, and now it just becomes counting once, much simpler operation. And the nonlinear function of neural network just become sine function, once again, very simple. So the arithmetics of binarized neural network is really simple. So you can guess it goes very well with this idea of in-memory computing or near-memory computing or whatever, which would be to have your arithmetic that is closely integrated within your memory, because arithmetic is very simple, so you can really distribute it everywhere around your memory. So perfect for us. To be very clear, I want to insist that I'm here talking about inference hardware, because binarized neural networks are only really binarized once they have been trained. When you train them, which is identify the synaptic values that allow the neural network to do intelligent things, this training is actually done with synapses that have real weights. But once this training is over, you can forget this real weight and treat your synapses as purely binary numbers. And so that's really what we are doing. The idea is you can train your neural network on a big computer, and then you can transfer your binary weights onto a low energy efficient hardware to do new tasks with very, very low energy consumption. So how did we do that? So first problem, as I told you, is that we have to deal with, so of course, our idea is to use this new type of memory to store the synapses. However, as I told you, we have to deal with errors. And that's actually a very big problem. Because if we want to do this idea of in-memory computing, where we would have the memory and the logic that is very integrated close to the memory, if we have to use ECC, that means that we will have to replicate ECC decoding blocks everywhere. And unfortunately, as I told you, ECC decoding is actually quite complicated. On the other hand, the arithmetic of binarized neural network is very simple. So you would end up in a situation where most of your area and most of your energy consumption would be dedicated to detecting and correcting error. And of course, that's not really satisfactory. So we wanted a solution without ECC. And this is what we did. This is our test chip. So this is done in a process by Leti. You have your memory, so in a 130 nanometer CMOS process, and you have your memory stores that are based on hafnium oxide that are here between metal 4 and metal 5 of layer. So it's kind of partially industrial, partially academic process, but that allows to test real designs. And we fabricated this memory array that has resistive RAM and all the periphery circuit behind it. And this is a picture of the test chip. And the particularity of our design is that for storing one synapse, we do not use one memory stores, but actually two memory stores. And why do we do that? We do that because we program synapses actually in a complementary differential fashion. Meaning that if we want to program weight +1, we program the first device in low resistance state and the second device in high resistance state. And if we want to program weight -1, we program the first device in high resistance state and the second device in low resistance state. Then when we want to read synaptic weight, we can use this type of sense amplifier, which is very efficient, which can actually compare the two resistance values. So why is that a good idea? Because we could have used actually only one device for storing a weight and having maybe low resistance state meaning -1 and high resistance state meaning +1. We believe it's going to really reduce errors because actually for an error to occur in this scheme, you need a device that was intended to be low resistance state, to end up with a resistance that is higher than a device that was intended to be high resistance state. So to a large extent, that means you would need both devices to fail. So you imagine that if your failure rate is something like epsilon, now your failure rate for the weight should be something more like epsilon squared. So you should be able to reduce your errors, of course, to the cost of doubling the number of devices. Another benefit of this scheme that does not use DCC is that we can do what we call logic in memory. Actually, if you take our sense amplifier circuit and you add these 4 transistors to the sense amplifier, you can look into it, you will realize that the output of the sense amplifier will not be the weight, but actually the XNOR between the weight that is stored here and the input that is applied here. So that means that this circuit can do the XNOR operation at the same time as it senses the value of the resistive memory. And if you remember what I said before, XNOR is the equivalent of multiplication in a binarized neural network. So does this work? So here are some measurements on our test chip. So what we did is that we plot here on the y-axis the bit error rate at the output of the sense amplifier using our strategy with 2 memory stores per synapse. On the x-axis is the error rate that we would have if we had used a single device per weight. And we have many points because we programmed the array many times in different programming conditions so that we would have different error rate. So if our strategy had no impact, the red points would be on y equal x line. And you see they're actually below, quite close to the y equal x square line, which shows that our strategy indeed reduces the number of errors. So we were very happy with this. But to understand the extent to which it is useful, it is important to still compare with the more traditional approach, which is DCC. And we compare with a very simple code, which is a single error correcting, double error detecting, or extending HAMI, because it's probably the only one you could consider using in a memory computing context, because it's still not that difficult to correct errors. And if you take ECC that has the same degree of redundancy of hours, which is doubling the number of devices, so that's the green curve, you can see that the impact is actually very close to our strategy. Except that in our case, we do not need to detect or correct error. Everything happens within the sample amplifier when you rinse the device. Whereas here, you will need this extra circuitry that will dominate area and energy consumption. But nevertheless, you can notice that the final error rate with these kind of approaches and with our devices, so of course it will be different with different kind of devices, remain quite high. I mean, we have still significant error rates by the standard of digital electronics. So it's also important to understand to what extent these errors need to be corrected. And this is also something that is extremely interesting. So here we simulated binary neural networks that are trained to do different tasks. So first you have MNIST digit recognition, then you have CIFAR10 image recognition, and then you have ImageNet image recognition, which is a very difficult task. And what we did is that we introduced artificially errors in the binary ways to see the impact on the AI tasks. And so the x-axis is the amount of errors that we included, and the y-axis is the accuracy on the AI task. And fascinating, you can actually tolerate quite a high number of errors. So actually, with 10 to minus 5 bit error rate, which is very high by the standard of digital electronics, you can see, well, you cannot see actually, but it is indiscernible from simulation with no errors. And then even if you have really high bit error rate, so that's 10 to minus 3, the accuracy has actually decreased a little, but really not that much. And 10 to minus 4, there is practically no degradation. Only 10 to minus 2, you can see you have accuracy that really starts to degrade. So actually, you do not need to correct all errors. Even if you have significant amounts of your weights that are wrong, your application will still work. And that's really good because you can see we have a strategy that reduces the number of errors without ECC, just with the differential approach. And then actually the final error rate you need is actually not that high. So that means that you can use devices that are initially very, very, very bad. Because differential will reduce bit error rate, and you can still be in this range that is not so good. And actually, working with devices that are very bad, counterintuitive, but it can have some big benefits. So here are examples on our resistive RAM technology. So here are typical conditions that you could use. So you use quite strong current and voltages to program them to have relatively low bit error rate. And unfortunately, this type of programming condition results in high power consumption and devices that you cannot program too many times. After having been programmed 10 to 8 times, typically you cannot program them anymore. If you use these programming conditions that have actually lower voltage, you have bit error rate that is going to be higher, but still okay for binary neural network. But now your devices are much more endurant. You can program them 10 to 10 cycles. Alternatively, if you use these other programming conditions where programming times are shorter, you get bit error rates that are higher, but still okay for binary neural network. But now programming energy is much more attractive. So that means that if you accept to use devices that are very bad, you can have big benefits. So either in terms of endurance or in terms of programming energy. So these are specific numbers for our technology, but the same kind of things can be seen on phase change memory, on magnetoresistive memory, or actually even on SRAM. It's actually well known. If you reduce your voltage, you are going to have some errors, but big benefits. So yes, point I want to make, if you can use bad memories, that's nice. So we are making progress. So now we have made, so what I showed was based on a single array. Now we have made a whole system that we are currently finishing testing, that we should be able to do soon. Particularity is that this system fully digital, because arithmetic of binary neural network is so simple. We do not use Kirchhoff law, as must have been presented in some other talks of these seminars. And soon,
Damien?
Yes.
Sorry, can you ask some question clarification?
Sure. Is that okay, Nima?
Yeah, if it's quick and ready to.
Just for the understanding part. So this whole thing is for the computer vision MLA DL, right? It's not, you don't have other models, right?
Sorry, I actually did not understood you.
So okay, let me repeat myself. All this is assumption is for the computer vision part of the AI or DL or ML workloads.
Yes. Yes.
Other workloads, NLP or any other workloads, this is not applicable. I understand it correct?
Yes. So actually, we are working on other type of ML as well. We're also very much working on Bayesian reasoning or probabilistic graphical models. But yes, it's pure. So this type of error tolerance is very often seen in machine learning. I do believe it could be also applicable for image processing or some type of signal processing where you could see this type of error tolerance, but you do need some error tolerance at the application level, which is of course not for every application.
Thank you.
Welcome. So here is also some estimates of energy benefits of this type of approaches for inference. So here I look at the energy for recognizing a single MD digit, which on a CPU or GPU is typically millijoule energy consumption. And now if you look at what the consumption of our system would be, so this is simulation, this is not a measurement on our actual system. So these are the points here for the BNN on a whole system with validation, with inference energy as a function of the validation accuracy, the accuracy on MNIST recognition. And I compare here with ANN, that would be the neural network that would be implemented with 8-bit integer operation, which is what is often done for edge system. But here, it's not a full system. I only take into account the arithmetic operation. And it's important to do this kind of comparison because binarized neural networks, actually, to have equivalent accuracies than normal neural networks, you need more synapses. But nevertheless, you can see we can get big energy benefits because full system, even compared with only arithmetic operation, energy is a lot lower. However, we can also see that this difference depends a lot on the accuracy that you want. And so, yes, in this kind of design system, you really have to design for the type of accuracy that is important for your application. There is some, sorry. So possible application for this kind of things, we see a lot of potential for medical type application. So actually, people envision a lot of application where electronic people could wear some kind of sensors, and the systems would be able to have big benefits, like being able to detect or predict stroke, epileptic seizures, or even heart attacks. And what would be really important is for this type of systems to be truly autonomous, to not rely on the cloud, because for such medical application, yes, that would be a concern in terms of privacy and security. But very big problem for this type of application is, of course, the high energy cost of AI, which is not very compatible with such extreme edge application. And so we believe this kind of approaches would be very favorable for this. And we have started to kind of look into that. So for example, we have trained binarized neural network on data set coming from medical application. So we have one data set employing ECG, so electrocardiogram, and one from EEG, which is a brain signal. And so we took this kind of traditional tasks, which are not directly medical tasks, but are representative of tasks that involve this type of signals. And we trained binarized neural network, and we could get accuracy that is very close to neural network relying on 8-bit precision, but with very big memory saving. So we are quite optimistic this kind of approaches can be used for this type of medical application, and we are very much interested in collaborators on this type of topics if you are interested. So that's what I wanted to show on this first project, which is to show these circuits that work even if the devices make errors. But now I want to go to more futuristic research, which is to actually turn the point of view on this device and to try to even exploit their imperfection. And on this research, I'm not going to talk anymore about inference hardware, but on learning hardware. So systems that are actually on the edge using memory store, able to learn new tasks. And actually, training neural networks with memory stores is a task that is extremely difficult. Because to do that, as I told you, we cannot use purely binarized synapses. Actually, we need real weight. And a very traditional thing that is looked at in the literature is to actually use your memory store as analog memory and to store your weights in an analog fashion. I think you had talked about this before in this series. And if you want to train neural network in these conditions, that means you need to kind of change the resistance of your device while you train your devices. Traditionally, training neural networks is done by the algorithm of backpropagation. But the big concern is that algorithm of backpropagation functions by showing example to the neural networks, and then you make some calculation, and that tells you tiny changes that you need to do to the weights of your synapses, and therefore to the resistance of your devices. Unfortunately, because memory stores are so imperfect devices, doing these very tiny steps is actually very challenging. So actually doing error backpropagation on memory store is a very difficult problem. So there is a lot of research on this. So we are actually working on this as well. There is some progress, but it's still a very difficult problem. And here, I want to show a very alternative approach, which is to do the training in a totally different way using another type of algorithm, which is called Metropolis-Hastings Markov-Chain Monte Carlo. This type of training algorithm functions very differently, because the idea is that you start from a random model, and then you need to create new versions of the model. And to create these new versions of the model, you actually do not make tiny changes to the conductance. You need actually to sample new models in a random fashion. So that means that your new model should be the new values of the weight should be random values that are based on the values in the previous model. And then you get a new random model, you make a test on it, and if you accept it, you keep this model, and then you generate a new random model, and so on, and so on, and so on. And then at the end, you end up with a collection of models that you can use to make prediction. So you can see it's very different. Now you do not need to make tiny changes to the conductance. You need to actually generate new value of the conductance in a random fashion. And actually, I told you, every time you program a memory store, you end up with a new resistance. So actually, you can start maybe to see where I'm going. I'm going to be able to use the variability of the device, the fact that every time you program it, you get different resistance, to actually implement this sampling step where in MCMC, you need to generate new models. So here are some measurements that show how this is going to work. So these are devices that this is a device that we program many times in a low resistance state. So here this is actually programmed at conductance, inverse of the resistance. And this is the distribution of the conductance you get. And you can see it follows a beautiful normal law, Gaussian, which is actually exactly what you need for MCMC. And if you plot the mean value of this Gaussian and the standard deviation of this Gaussian as a function of current, you get this curve, which shows that you can actually control the properties of your Gaussian. So that means you actually have a device that will very naturally sample a new value of the weight and keep it in memory, which is exactly what you need for MCMC. And so once we had this intuition, we wanted to try that. So here is how the system is going to work. So I explained in broad terms, but if you want the details, they are in our recent Nature Electronics paper that was published, I think 2 months ago. So we use a memory array, and the idea is that each row of the memory array is going to represent one version of the model. So initially, everything is random, and then you need to program the next row of the model based on the previous one. And so this is done in a very simple way. You use the current that flows through one device, and you inject it into the next device, and so that will reprogram the device with a new conductance, with the mean that is the same as the one you had before, but this is a new random value following a Gaussian law. And this is a simple principle, but we actually tried it in practice using an array of 16,000 memory stores. In our experiment, we use a real array, but we don't have yet all the periphery that goes with it. So the periphery, so in particular accepting or rejecting the model, is actually done on a computer, emulating what the periphery would be, but everything that involves the memory store is done within the memory array to check that it can work with the level of imperfection we have in memory store. And we trained this way a very simple neural network to recognize either cancerous or non-cancerous images. And here are the results we get. So this plot represents the final state of the memory. The colors are the different conductance level. And so the rows are the different models, and the columns are the different weights. So if you look, for example, in a single column, that you can see all the values that the parameter are as different in the different models, and you can plot their distribution. So you can see each weight has a different distribution that does not look the same. And then you can use each of these models independently to recognize images if they're cancerous or not. So if you look in this graph, what you have is the accuracy of each model as a function of the row number. And you can see that all the different models have different accuracy. Some are quite accurate, some are less accurate. But if you pull them all together and you match and to make a final decision, you get an accuracy of 98%. And so our system can recognize if an image is cancerous or not 98% of the time, which actually matches what is possible with software. So we are very happy with it. We have a system that learns with memory store imperfection and that can recognize cancerous images. Let's talk a little more about what this means. First, I want to highlight that this type of learning is special. So you do not end up with a single neural network, but with a collection of neural networks. And so what you end up is actually called a Bayesian model, meaning that your output is not really going to be a single output, but a distribution of output, which is all the outputs of all the neural networks. And this type of Bayesian neural networks has some very nice features. So for example, a very big challenge in traditional neural networks is that they are quite bad at being able to tell what they don't know. Like for example, if you have trained a neural network on digits and you present the image of a cat, the neural network will make a prediction, like maybe this is a 3. But on the other hand, a Bayesian neural network will give you a distribution of possibilities. And in this case, it will probably give a quite flat distribution, showing that all possibilities are equivalent, and really the neural network does not know what it's looking at. Of course, Bayesian neural networks are not applicable for everything. And in particular, you can guess already, because you have multiple versions of the same neural network, they are actually not very adapted for very big data world where you have a lot of parameters. So they are more for the small data world, where you don't have that much data to train on, and you have a lot of uncertainty. Then this type of neural network will be able to deal very well with this type of situations. They will not overfit like normal neural network, and they will be able to tell you their certainty about the result. So this can be very good, for example, for medical applications. That's why we chose this cancerous image example. So yeah, it's like backpropagation is more big data. Bayesian is more small data. So in our papers, we have some estimates about energy efficiency. So we have some elements, although the system is not entirely fabricated. First, we can see that if you compare with a system that would have been trained on backpropagation, our system actually requires less programming operation on the memory stores. It's a little counterintuitive, but because Bayesian neural networks are more adapted for small data tasks like this one, they actually end up requiring less operation. Also, we have not so fabricated the periphery, but we have designed it and simulated it, and that allowed us to make estimates of how much energy final system would consume. So you can see in our 130 nanometer technology, for doing one task that is in our paper, it will require 7 microjoule to train the model, and 3.6 microjoule in a 28 nanometer technology. It's not that different because we rely significantly on analog electronics. And by comparison, Xeon processor required 600 millijoule to train the same model. So it looks very favorable. Other thing is that, so of course, our system uses device imperfection, but it uses one type of device imperfection, which is the cycle-to-cycle variability. But there are other types of device imperfection, like the fact that resistive memories age. We program many times, it changes their properties. So we wanted to check to what extent our system is robust to this type of imperfection. So what we did is that we actually took the array, so we test it, and then we reprogram the memory devices many times. For example, here, all the devices have been reprogrammed 1 million times. And you can see that if you retrain then the cancerous image task, the accuracy is still almost as good as it was initially. And this is to estimate with 10 million times. Actually, we cannot program all the devices 10 million times because our experiment is too slow, but we use error rate after 10 million times, and we project that it should still work just as fine. So yes, this kind of scheme that exploit device imperfection. So typically, they are quite robust even to other type of imperfection, but you have to make sure of it. So we approach the end of my talk. So I explained in detail this work, but I wanted to highlight that there are other projects that turn things around and exploit imperfection of novel memory devices. So I just mentioned this to give some literature. I'm not to explain in details. For example, there are applications where you really need randomness. So you have, for example, true random number generators. And for example, we have this work where we actually use the stochastic properties of MRAM to generate true random numbers at very low energy. And you also have many applications. So I think this paper is from Dmitry Strukov that uses the stochastic nature of memory stores to generate physically unclonable function, which is another type of application where you need this randomness. And both of them are strong implication for hardware security. We also have a variation of our Bayesian work that is not for learning, but for inference, where we actually exploit the imperfection to program the neural networks in a good way. And there are also some beautiful works that use the imperfection of spintronic magnetoresistive devices to actually do some kind of optimization, the fact that the devices can switch all the time, and they can show it's a very strong source of computing power, and that it could be used to do quite difficult computing tasks. This concludes my seminar. So I wanted to highlight that binarized neural networks are excellent candidates for in-memory computing with emerging memory, and I really wanted to insist on this idea that is true on SRAM on some extent, but that is extremely true on emerging memory, that embracing bit errors can have important benefits in terms of programming energy, indirectly cell area, and reliability. So you do not necessarily want your devices to perfect. And I wanted to also highlight by this, showing this futuristic work that the statistical nature of devices can even be turned around, not be a total problem, but a source of feature. for example, for learning Bayesian model. So I thank you for your attention. And I also highlight, I am hiring some postdocs. Not all the offers are online, so do not hesitate to contact me.